Welcome, ladies and gentlemen, to Integrated Math 2. In today's episode, we will be discussing Chapter 4.1.5, which is Factoring Special Cases. This section deals with special quadratics, and actually we've encountered them in the last couple sections, and every time we encountered them, I made sure to pause for a second and give it a very special name. And hopefully, if you have been keeping up, you will know the names of those quadratics, and we'll go into more detail on what they actually are. First off, in 4-45, they're going to want us to factor each and every one of those quadratics right there. Now, I'm going to go ahead and just pause for a second and write down the answers without doing the area model. Hopefully, you guys will pause and do each of those with the area model. That way you know and have practice with it. But I will be back in just a flash with the quadratics that are already factored, and we'll talk about which ones are the special quadratics. I'll be right back. And here we go with the quadratics that are already factored. Now, what I'm going to do is I'm going to go through and I'm going to put a star next to the ones that seem different than the others. This one seems different than the others. This guy does. This guy. Let's see. This guy. This one, and this one. Why is it that the ones with the blue stars next to them are different? Well, the ones with the blue stars next to them are different because they represent either what I called in the last couple of videos a perfect square trinomial or a difference of squares. Now let's go ahead and define what those look like. A perfect square trinomial I'll go ahead and give you a couple of the examples of those from this array of problems here. So from here, 9x squared plus 12x plus 4 is a perfect square trinomial. Notice how he factors into 3x plus 2 squared. X squared minus 10x plus 25 is also a perfect square trinomial. Notice how he factors into x minus 5 squared. And so let's just do one more just because I feel like it. 4x squared plus 20x plus 25 is another perfect square trinomial. Again, he factors into 2x plus 5. So the way I've always recognized a perfect square trinomial is if you look at the front end and the back end problem, or the term, these terms here, oops, I don't want to cover the squared. These terms are often perfect squares. In fact, they're always perfect squares. And the way I've often factored them is I look at this as a singular 2x that's all being squared and a 5 that's all being squared. Notice how these terms show up in the factors and they're all collectively being squared. Now, the way to factor this really quickly is to look at the symbol surrounding the second term. Notice how when the symbol in the second term is minus, it's going to be negative. When the symbol next to the second term is positive, it ends up being positive. And I'm just taking one of each from each bracket. So factoring a perfect square trinomial is actually pretty easy as long as you can recognize the pattern. So again, the first and last terms are going to be perfect squares, and at that point you can almost just square root both of them and put them in and square them as a collective. And of course, if you're not sure, you can always just re-multiply it out and check it out. So from here, if I was to do the same process with g, right? If I was to see this as x squared minus 6x plus 9, if I saw this guy as x squared, because there's nothing else about him, but I was to call this 3 squared, then we could ultimately call this guy x and 3 all squared, and then how do I determine the sign? Well, I look at the sign of the middle guy. It's going to be minus. And there we go. These are our factors right here. So that's what a perfect square trinomial is. Now, contrast that to what we call the difference of squares. And I'll go ahead and put that down in the same color, the difference of squares. The difference of squares, on the other hand, will be something along the lines of A. So x squared minus 49. Again, we saw that factor into x minus 7 times x plus 7. We saw, let's see, x squared minus 36. And that factored into x minus 6 times x plus 6. Now, similar to the perfect square trinomial, a difference of squares will factor into the same terms in both brackets. The difference of between the two, though, is notice the opposite signs happening here. Notice the opposite signs. Unlike the perfect square trinomial, which had the same signs happening here, which is why we were allowed to consolidate all of our perfect square trinomials into a collective thing being squared. The difference of squares will not do that, and people will make the mistake of trying to consolidate the x plus 7 times the x minus 7. They can't be consolidated. This is as simple as they get. And so please make sure we are keeping the difference between difference of squares and perfect square trinomials. A difference of squares realistically is just two squared terms that are perfect squares, and they're being subtracted. So perfect square here, perfect square, and then subtraction. Subtract. And that ends up being your difference of squares right there. And so from here, let's go ahead and define using a more book-based definition of what a perfect square trinomial is. A perfect square trinomial is a trinomial that always turns into a squared plus 2ab plus b squared. So notice how the first and last terms are being squared. So these are your perfect squares. Perfect squares. And then this is 2 times the first and last term. So 2 times the first times the last. So again, how do I get this? So 3x squared is 9x squared. Cool. 2 squared is 4 squared. So I'll go and write that out here even larger. So 3x plus 2 squared. If I do the entirety of 3x squared, I get 9x squared. If I do the entirety of 2 squared, I get 4. Now, AB is going to be these two guys multiplied. So what's A times B? Well, that's going to be 6x. But I'm going to multiply him by 2, and that gets me 12x. And then positive, positive. And there we go. And notice how we're back to where we started. A difference of squares, on the other hand, is going to be simply, and I'll go ahead and just bracket them off down here. This is going to be a squared minus b squared, where again, you have perfect squares being subtracted. So perfect squares being subtracted. The importance of recognizing the perfect square trinomial versus the difference of squares, among other factors, is that when you see one, you don't necessarily need to do the area model anymore. It will actually speed you up if you don't do the area model, if you can recognize the difference of squares in the perfect square trinomial. So just be on the lookout for them. And yeah, I think that will wrap it up for this part of the lesson. I'll be back with the next part. Give me a second. The next type of factoring that I want to go over actually isn't covered by the curriculum, but it is, I put it in here because it's a special case, but not something that's recognized by this book anyway. But it's called factoring by grouping, and factoring by grouping is used to factor the 4-part polynomial. It's used to factor a 4-part polynomial, and so let's see what that looks like here. Now, up until now, we've been dealing with trinomials at max, which is 3 terms. The 4 term will look something like this: 2m cubed plus 6m squared plus 3m plus 9. Now notice how there's 4 parts here. So it's easy to get threatened when there's more than 3 parts. Now the area model is going to be a little bit different. We're not going to use the area model for this one, but that's okay. We're going to bring back a technique that we learned in the last section here, and it's going to come back and it's going to help us out a lot here. The idea of the factoring by grouping is I'm literally going to group the front 2 pieces versus the back 2 pieces. And what I'm going to do is I'm going to factor out the greatest common factor between the front and factor out a different, possibly, greatest common factor from the rear. So from the front piece here, I'm going to use the greatest common factor, or GCF. I'm going to GCF out a 2m. What does that leave me on the inside? Well, remember, GCF factoring is division. So I'm going to go and divide each piece by 2m. That's how I'm going to get my inner pieces here. That's going to leave me with an m plus a 3. Again, if I just divide all the pieces out. From the right piece, or from the chasing piece, or the back piece, looks like I'm going to factor out a 3. Notice how I kept that sign positive right there. I'm going to factor out a 3. Well, what does that give me on the inside? Well, again, it's an m plus 3, exactly like this guy. So now what happens is the 4-part polynomial becomes now a 2-part polynomial. You see how I only have 2 terms now being added. So now there's a different GCF. It's a GCF within a GCF. So what I'm going to do is I'm going to factor out the GCF of the new polynomial, which is m plus 3. And remember, when I factor out a GCF, I am essentially dividing. And when I divide, that leaves me with 2m plus 3 on the inside. And that is factoring by grouping right there. That is how a 4-part polynomial becomes a 2-part polynomial. So I'll probably do 3 more examples, and then that'll do it. So from here, I'll go ahead and do this one here. So let's go with 14x cubed plus 21x squared plus 16x plus 24. Group them off. So front runner, looks like I'll factor out a 7x squared. And what does that get me on the inside? Well, if I factor out a 7x squared, I'll literally go ahead and divide it. That gets me 2x plus 3. From the rear here, it looks like I'm going to be able to factor out an 8. And that's going to get me a 2x plus 3 on the inside here. Again, notice the 4-part polynomial now becomes a 2-part polynomial, right? And so from here, I'm going to go ahead and factor out the 2x plus 3. So factor out the 2x plus 3. And again, by factoring, I am literally dividing the terms out. So if I divide those terms out, I'm left with 7. Whoops, why is there a plus right there? 7x squared plus 8. And there we go. That's our second example. I'll go and do another one. So let's go and do this one here. This is 27x cubed plus 45x squared minus 3x minus 5. This one's going to be a little bit different here. I'm going to go ahead and block them off. From the front runner, it looks like I can factor out a 9x squared. If I do that, that's going to give me 3x plus 5. Now, if you look at the rear end polynomial here, it doesn't look like I can factor anything out. So what I'll do is I'll factor out a negative 1. And what that gives me is 3x plus 5. And so if you're wondering, why did that happen? It's a great question. Well, remember, if I factor out a negative 1, what's happening here is if I redistribute the negative 1, I'll get the negative 3, which is what I had before. If I redistribute this 1 here, I'm going to get a negative 5, which is what I had before. If you remember, and you can even rewind the video, the original polynomial was 27x cubed plus 45x squared minus 3x minus 5, like that. If I redistribute, I'll get back to where I started. And so now from here, again, I have a 2-part polynomial. I'll go and factor out that 3x plus 5. Now this is an interesting polynomial because from here, it seems like I'm done, but I'm not, because in the last lesson, we talked about factoring completely. This guy can refactor into 3x minus 1 times 3x plus 1. And so that is what this thing looks like when it's factored completely. All right, let's go and do one last example, and then we will go and wrap up this factoring by grouping here. So let's go and do this one. 12m cubed minus 32m squared plus 6m minus 16. If you want, feel free to pause and try and beat me to the answer. No worries. Until then, I'll go ahead and just group them off. From the front, I think a 4m squared comes out, so that gives me 3m minus 8. From the rear piece, I think looks like a, 2 comes out, so I have 3m minus 8. Now that I have my two-part polynomial, I'll go and factor out the GCF, which is going to be 3m minus 8. And you're left with 4n squared plus 2. And there you go. That is factoring by grouping, and that will conclude your factoring special cases. As always, please leave comments or questions in the comments area, and I will see you all in the next episode.